Hi, and welcome to Earie's 8-Bit Workshop. I'm Earie Salmon, this is my workshop. Have you ever pulled a chip from an old computer and gone, I wonder if this thing still even works? When repairing or building retro systems, one of the biggest unknowns is whether your logic chips, your DRAMs, your SRAMs, whether they're still working. In this video, we'll look at 4 different ways to test ICs, from quick and dirty probing to dedicated testers, and even modifying the testers to suit unknown chips. By the end of the video, you'll know the strengths and weaknesses of each and which one might be right for your bench. First, let's see how logic ICs work in a demo circuit. Here's a diagram of a circuit I have on a breadboard. I've set up a 74LS08 AND gate and 2 inputs driven by a counter coming from the LS74163, which is driven by a clock from a 555 timer. The output goes to an LED so you can see the result. Seeing the board in action, you'll notice the LED is on for a count of 3 and off for a count of 1. I'll start with a very simple and cheap multimeter oscilloscope. If I hold and press R while on a voltage test, it switches into oscilloscope mode. I'll place the black probe on the ground rail here and watch as I probe input pins 1 and 2 with the red probe. You'll see them go high and low on the screen. What they're doing is stepping through 00, 01, 10 and 11. Now look at the output on pin 3. The LED only goes out when both inputs are high, as this is an AND gate. But this is where things get tricky. In a real circuit, when you probe inputs and outputs, you can only see one signal at a time. Although seeing 2 or even 4 is possible with real oscilloscopes, interpreting the information you're seeing, not to mention holding all the probes in place, is very difficult. You might miss glitches, bus conflicts, or even issues hidden by pull-up resistors. For example, if I were to let the input float, the output can seem stuck or flip unpredictably. Sometimes external wiring or other chips mask a fault, making a good chip appear bad and vice versa. So how do you check if there's a bus conflict or a floating input? So here's what I do. To detect a bus conflict, I probe the line with my scope and my logic probe, while also carefully toggling or disabling connecting chips if possible. If the voltage level unexpectedly jumps or glitches between high and low erratically, or if 2 chips seem to be driving the bus simultaneously, that's the sign of a conflict. Pulling the line gently with a resistor to ground or power can also help to see if the chip output is fighting another driver. For floating inputs, check if the input pins are unconnected or if they have no definite high or low level by probing with your scope. Floating inputs often show noisy, unstable signals that jump randomly or hover near threshold voltages. Adding a pull-down resistor, for instance a 10k ohm, to ground can stabilize the input and clarify if the chip was misbehaving due to floating. Another trick is to manually drive the inputs high or low with a jumper wire or switch to isolate whether a chip is responding correctly. With memory ICs such as SRAM or DRAM or EPROM, a probe only tells you if the lines are active and won't verify data integrity. For that, you need dedicated testers. Remember, in-circuit probing is fast and free but can be misleading. Bad wiring or other chips can trick you into diagnosing a good chip as bad or fail to detect a hidden fault. For example, I'm going to swap out the 74LS08 with one that exhibits an odd problem. Watch the speed of the LED. That's odd, it's flashing at a more regular rate rather than being mostly on. If I probe the inputs, they don't seem any different, yet the output has definitely changed. This is because this particular chip has wedged one of the inputs high. We can tell that this is a problem because we know what to expect from the output. But since we can only probe one signal at a time, all we can see is that the input lines and output lines are toggling between 1 and 0, and in a real board, the chances are we'd miss this problem thinking that the IC is fine. Have you ever been fooled by a chip, passing as a logic probe test but failing elsewhere? Share your story or tips in the comments. What's your favourite in-circuit troubleshooting trick? Next up, the Retro Chip Tester Pro. This is a dedicated device built for retro repair. Pop your chip in the ZIF socket, choose the IC and logic test, and select the part number, in this case the 74LS08. The tester runs through all the input combinations and reports pass or fail. Here is the strange logic IC from the breadboard. We can now see exactly what the failure was. It also supports common static RAMs like the 6264 and the 64256. You can write and read test patterns, which is really handy. And for ROMs and EPROMs, you can read the contents, dump them to a file. Perfect for checking whether a boot ROM against a known good binary. It has adapters for SIMs, cartridges, PLAs, and many others. But you do have to remove the chip from the board, and if you're desoldering, I'd recommend installing a socket to save time later on. So, strong for logic and a wide variety of memory. In fact, new ICs are constantly being added to the RCT Pro via firmware update. I've done a video on how to update it using a Mac, and I'll link that to the video at the end of this one. The TES is like a budget version of the RCT Pro. It handles logic ICs, but the library is much smaller and the menu system is very clunky. Some units claim support for SRAMs or EPROMs, but in practice it's unreliable. Here is an example of a chip that we've already tested and know is good from the RCT Pro, yet fails on the TS200. Here's the chip which we know was bad. Well, at least it got that one right. So this one's fine as an entry-level tool, but you can't always trust the results. So here's a little bonus IC tester. I haven't included it as a main feature, simply because it doesn't appear to have a recognizable manufacturer or model name. It's just a cheap unit that I picked up from AliExpress to test some of the more obscure op-amp ICs. Let's see how it does with our test chips. Well, the working one reports OK despite the TES200 results. And the broken one reports bad. So already we're ahead of the TES200. Let's try it again, but this time do it at the other end of the ZIF socket. Oh, well, that's irritating. I guess that's what comes of not having documentation. Let's try the bad chip, see if that actually fails. And it did. I don't know why they wouldn't put it in the standard orientation, but at least it works. Our fourth method is the TL866. Many people know it as a device for writing EPROMs, but what a lot of hobbyists don't realise is that it can also test logic ICs, RAMs and ROMs. Here I've just tested our known good 74LS08, and minipro has displayed each test result and it passes. Compare it to these results from our bad 74LS08. We can see the exact test and which gate has failed. We can also extend minipro's definitions. I work a lot with Acorn computers, and Acorn seem to love using the 81LS95, which is an octal buffer. Although there are equivalent in the 74 series, I guess they weren't around at the time. If I want to test with minipro, I'm going to need to extend the definitions. Fortunately, it's quite easy to do so. First, locate the truth table in the product sheet. Then open the logic.ic.xml, go to the end of the file, and add the definition for our 81LS95. Each vector line is a test. 1 indicates the IC should be given a voltage on that pin, 0 indicates it should be grounded. V and G indicate the voltage supply and ground supply to the IC. H, L and Z are the chip outputs of 1, 0 and high impedance. This is what the completed vector table of the 81LS95 looks like. Let's test it. We see here that the 81LS95 custom IC is now appearing in Minipro's index. Let's start the test. Oh, my IC could be faulty. Or maybe I've made a typo on the vector. Let's double check. Yes, 4-pin outputs are incorrect. Let's test again. Now the test succeeds. Now you might wonder why I didn't have to have any Zs in my definition. Well, that's because I've cheated and I've taken a shortcut. If G1 or G2 input pins are high, then we shouldn't care about the IC output. Z is essentially undefined. I could put in a complete set of tests into the XML to include all of the tests where G1 or G2 are 1 and validate that. But after looking at the 74LS244, which is functionally equivalent, albeit with a different pinout, this is how it was tested there. Now I mentioned that the TL866 can be used to test memory ICs too. Unfortunately, this is where Mac and Linux users who use minipro are a little let down. There doesn't seem to be any way of testing SRAM or DRAM with minipro. For EPROM ICs, we can dump the content and use a checksum to validate the dump against a known good image. Windows users have it a little easier. As I understand it, XGECU does allow some testing of memory ICs on Windows, but it's not available on other operating systems. So minipro and the TL866 is a powerful utility for testing. And here's where we stand in summary. So which method is best? Well, for quick tests in circuit, there really is nothing better than an oscilloscope. If you don't have an oscilloscope, then a digital multimeter with an oscilloscope mode can do the job, and failing that, a logic probe. But for more thorough testing, you're going to have to remove the chip from the board. And once you've done that, using the RCT Pro is definitely the way to go. The TES200 can do some more obscure chips like 555 timers and other operational amplifiers. But for the majority of chips you're going to be testing, the RCT Pro is exactly what you need. Comment below on what tools you use. I'd love to know. Well, I really hope you've enjoyed this video and found it useful. Please do remember to like and subscribe for more retro tinkering, and I hope to see you next time on Earie's 8-Bit Workshop. Goodbye.